So here's a problem that you typically see in a calculus class where you've got an inverted cone in the shape of a right circular cone with some kind of base radius and height given. In this particular problem, gasoline is being pumped into the tank at the rate of 8 cubic meters per second. Find the rate in meters per second at which the gasoline level is rising when the gas is 4 meters deep. Okay, so over here on this blue triangle, that represents a cross section of the inverted right circular cone that's passing through a diameter of the base, perpendicular to the base. So this red line here represents the height of the cone, which is given as 5 meters. And this distance right here represents the base of the radius of the base. And then the idea is that the gasoline level is rising as gasoline pours into the tank at this rate of 8 cubic meters per second. So this green circle represents the top of the gasoline at a given point in time. And so the area, or the volume, is represented by what's everything down in here. The key to this problem is realizing that we've got two similar triangles here, okay? Because of the fact that we've got right angles in the triangle. I actually could call this point A, this point B, and this point C. So triangle ABC is similar to, let's say, PQC by angle. They've got an acute angle equal right here, and they've got a right angle. So the fact that those two triangles are similar means that their corresponding sides have the same ratio. They're in proportion. So it's true that 4 is to 5. The legs of the triangle are in the same ratio as R is to H. And that means we can write R equals 4H over 5. So now remember that as we move over here to talk about the formula for the volume of the gasoline at any given point in time. We're using the formula volume equals 1/3 pi R squared H, formula for the volume of a right circular cone. And the key is that we want to get this down to a function of H, so that when we take the first derivative, we'll end up with the derivative of H with respect to time, which is what we're trying to solve for, this guy right here. So what we're going to do is plug 4H over 5 in for this value of R right here, and here's where that's been done. When we simplify this, we get eventually 16 pi over 75 times H cubed. So now the volume of this cone, the volume of the gasoline, is a function of H, the height of this cone from B to C at a given point in time. When we take the first derivative with respect to time, the derivative of the volume with respect to time, that's a rate that we know, that's given. That's this 8 cubic meters per second. When we apply the first derivative, or take the first derivative of the right side, we get 16 pi over 25 times H squared times the derivative of H with respect to T. In other words, if H is a function of time, it's kind of like using the chain rule here. We're taking the derivative of H with respect to T, and this is what we want to solve for. This arrow here moves us up to here where we're going to substitute in the values that we know, and solve for dH dt. We know that dV dt is 8 cubic meters per second. Technically, I should put the meters here and show how this evolves into meters per second, but we'll talk about that at the very end. I've left off the units. 16 pi over 25, we want to know what is dH dt when the height is 4 meters deep. So that's where this 4 came from, right here, when h is 4. Multiply this all out. I multiplied both sides by 25 to get 200 equals 256 pi times dH dt. Isolate the dH dt by dividing both sides by 256 pi. 200 over 256 pi reduces to 25 over 32 pi. And that is meters per second, because on this side I had meters cubed per second. When I square the height, I get meters squared. When I divide by meters squared into meters cubed, I get meters per second. And if you actually evaluate 25 over 32 pi on a calculator, you'll get approximately 0.25 meters per second. So there you go.